All right, guys, so we're going to go over this warm-up question, and then we're going to get into just a few more examples of projectiles that have been launched at an angle before you finish up the assignment that you began last week, 702.3 Mixed Projectile Motion Problem Set. That problem set was initially due last night, but because we didn't have school, it is due tonight instead. I have updated the due date on that. But let's go ahead and go over the question. It says, what height will a cannonball reach when it's launched at 90 meters per second at 40 degrees above level ground? Okay, we've already talked a little bit last week about how to handle questions when we have a projectile launched at an angle. So hopefully you remember some of that, but if not, then definitely follow along as we go over this warm-up question. So we're going to start by labeling some information that we know. We're looking for this top point right here that I've labeled with an X because that's what it says, what height will it reach. So we're looking at for that max height. That means that whenever I go to label things in my table, yes, I can label my vertical data for the entire time in the air, so from launch to impact. But I could also add in an extra column here to max height, or I could just have the column for max height and not worry about the total time in the air to impact for the vertical. But I'm going to go ahead and just add a third column to my table. Again, I've labeled them so that I know that this vertical data is going to be the entire trajectory, whereas this is only going to go to the max height. That way I can keep it straight. And I would encourage you to do the same if you're labeling it, especially if you're only going to max height. Make sure you label that so that you remember, oh wait, my time is only going to be half the amount that I have for my horizontal data. Okay, again, one of the first things that you need to do if you have something launched at an angle is to get the components. So it would help to start by drawing a triangle like this one. The question said that it's launched 40 degrees above the ground, so you'll notice I've labeled this as a 40-degree angle with the horizontal because the ground is, of course, horizontal. And I have my 90 meters per second here as that hypotenuse at that angle. But I'm looking for the X and Y components because if I'm trying to label all of my given information, I'm not going to write 90 meters per second anywhere in my table, because that 90 meters per second isn't horizontal and it's not vertical either. We have to find the components. Okay, and so that's going to be the first thing that we do, is start out by solving for the components. I'm going to start with this vertical component right here, VI, in the Y direction. And because it is opposite my angle and I know my hypotenuse, I'm going to use sine. I'm going to say that the sine of 40 degrees equals opposite VIY over 90, or if I rearrange that, it ends up being 90 times sine of 40 degrees. And again, if you are in degree mode, and hopefully you have a calculator and it is in degree mode, if you don't have a calculator yet, you might want to grab one. But when you multiply that, you get 57.85 meters per second, and that is going to be your initial vertical velocity. I know also, if I start filling in my vertical data, I know that my vertical acceleration will be due to gravity, negative 9.8 meters per second squared. And I know that that initial velocity and that acceleration are true regardless if I'm talking about the whole trajectory or if I'm just talking about the first half of it. It's still launched at that speed and it still has that acceleration. So I have filled those numbers into both of those vertical columns that I made. Okay, I also know whenever I look at the final velocity, if I'm looking at the entire trajectory to impact, if it's launched upward at 57.85 meters per second initially, then it's going to have a final velocity of negative 57.85 when it comes back down to the ground. Level ground, same height, we should have equal and opposite speeds there. Okay, so if it's launched at 57.85, it lands at negative 57.85. I know that if I look at the whole trajectory that my displacement vertically is 0 because I have started and ended at the same height. Okay, so my total displacement again from launch to impact would be 0. If I look over here, what would my final velocity be if I'm measuring just to max height, my final vertical velocity? 0. Okay, and so I can put that in there as well, 0 meters per second. I don't know the time yet, and I don't know the displacement to max height. That's the whole point of this question, is what height will it reach? So that's what I'm ultimately going to be looking for, but that's all I know so far, okay, with my vertical data. So now we can look at the horizontal. Again, if I want to find this component, and you could have found the components first for both and then filled in the rest of this, it doesn't really matter. We're just trying to fill in what we can. But if I'm looking for this pink component in my diagram here, VI in the X direction, again, this is adjacent to my angle, my 40-degree angle, so I'm going to use cosine. Say that cosine of 40 degrees equals adjacent over hypotenuse, that's VIX over 90, and then if I rearrange that, I get this. VI in the X direction equals 90 times cosine 40. Again, if you're in degree mode, that gives you an initial velocity in the X direction of 68.94 meters per second. Okay, and of course, if that's my initial velocity, that's my velocity everywhere, because horizontally, I don't have any acceleration, and so my horizontal velocity is constant. So I can fill in those other two values as well, that my final velocity is exactly the same. In fact, it's the same at every single point, and that my acceleration is 0. All right, so that is all that I know right now. I don't know any other information, but I know quite a bit. Just from, it doesn't look like they gave me much. They gave me 2 numbers, but I know all of these things from those 2 numbers. Okay, so again, ultimately we're trying to figure out how high this is going to go, but in order for me to do that, I need to figure out the time. Okay, and so we're going to start, or actually I don't have to get the time for that one, I'm sorry. We have enough information here to find just the height right here. Now, could I find time first? Yes, you actually don't need it for this particular problem because we already have these other 3 values here. So I'm going to use one of my kinematic equations. I have VI, VF, and A, and I'm looking for delta Y. I'm going to use the equation VF squared equals VI squared plus 2 times A times delta Y. It's the second equation on my board over there in black. And that's what I have up here, but I have the numbers plugged in. So VF is 0, so VF squared 0 squared equals 57.85 squared plus 2 times negative 9.8 times delta Y. And if I go ahead and start solving that, I move the 57.85 squared to the other side, I end up with this. Negative 3,346.72 equals 2 times negative 9.8 is negative 19.6 times delta Y. And then if we divide both sides by negative 19.6, we're going to get a positive number. And when you put that in your calculator, it comes out to be 170.75 meters. I filled it in here at the bottom. You're welcome to type it in yourself, but it's in my table now. Okay, so that is the answer. It's rounded, but that's the answer to the warm-up question, 170.75 meters. Okay, we actually didn't need the time there. Normally that's our first step. That's why I just automatically went there. And yes, you could have found it. You just didn't need it here. Does anybody have a question about the warm-up? Okay. Please make sure that you have entered your warm-up answer into My Open Math so that you're getting credit for this one today. And you should also have it, hopefully, as an example in your notes, because this is, again, just one more example of a projectile launched at an angle. All right, let's try another one. Again, you can copy this down if you'd like another example. This is very similar to the ones that we did last week and to the warm-up question. So if you're like, I already got that one, that's fine. The next one is a little bit different. But this one says a dodgeball is kicked 17 meters per second at an angle of 23 degrees above the ground. Find the time it takes for it to hit the ground and find how far away it lands. Again, when we see this question, we're going to start by looking at the fact that we have this thing launched at an angle. So I'm going to draw in my horizontal and vertical components of my initial velocity. That's 17 meters per second. Don't put it in your table. We need to solve for the components. So we need to figure out how much of that is vertical and how much of that is horizontal. And again, that means we're going to look at the trig, SOHCAHTOA, and we can solve for VIX and VIY. You'll notice I've already filled in my accelerations, negative 9.8 meters per second squared vertically, 0 meters per second squared horizontally. because those numbers are always true, so you can always fill those in. So let's go ahead and start with the y component. So again, sine of 23 degrees equals opposite over hypotenuse. It's the SO and SOHCAHTOA. I'm going to multiply both sides by 17, and I get this. 17 times sine 23 equals VI in the y direction, which is 6.64 meters per second. You'll notice I've already filled it in to my table. We're going to do for the entire flight this time. So you'll notice I filled in my final velocity as negative 6.64 meters per second. So why did I do the entire flight? Because the question didn't ask for max height. If it asks for max height, you obviously need that extra column. This one only wants to know the total time in the air and then how far away it lands, and both of those are for the whole trajectory. So I may as well just focus on the whole thing. I don't really need the extra column unless the question says what is the max height that it reaches, or if it asks something about the halfway point. All right, so I already have VI and VF. I know also that if I'm going from launch to landing that my vertical displacement is 0, so I went ahead and filled that in as well because again we're landing at the same height from which we launched. Let's look at the horizontal now. Again, we're going to use cosine because this is adjacent to my angle. Cosine 23 degrees equals adjacent over hypotenuse. Multiply both sides by 17, and that goes in your calculator. 17 times cosine 23, which is 15.65 meters per second. And again, that's a constant velocity, so I filled it in for both VI and VF because, again, my acceleration here is 0. I don't know the time. In fact, that's the first thing I have to find. Part A, find the time it takes. And I don't know my horizontal range, but again, that's the second thing I'm supposed to find, how far away it lands. So we're just basically trying to fill in the rest of the table. So starting with part A, the time that it takes for it to hit the ground, we're going to have to use the vertical data to solve for this because we don't have enough information horizontally. So if I look at my vertical data here, again, I have VI, VF, A, and delta X, which means I can use any equation up there as long as it has time in it. I can use it to find time because I know everything else vertically. The easiest one to use that has the fewest steps to solve is going to be this first one. VF equals VI plus A times T. And if we substitute into that equation, we can solve for time. But again, remember, we're only pulling from the vertical side. Okay, so don't pull from both. VF, again, negative 6.64 equals VI, positive 6.64, plus A times T, that's negative 9.8 T. Whenever you solve for this, your first step is to subtract 6.64 from both sides, which means you're basically doing negative 6.64 times 2. Which is negative 13.28 equals negative 9.8 times t. Divide both sides by negative 9.8. Of course, that negative is going to go away, and you're going to get 1.356 seconds. So the first part of this question, find the time it takes. That's the total air time, or the hang time of this dodgeball, is 1.356 seconds. And again, that is neither vertical nor horizontal. It's just time. I'm going to fill it into both sides of my table, because now I can use it to solve for the last piece, which is the horizontal range. Now that I know how fast it's going and the time horizontally, I can find the displacement horizontally. Going back here, if I want to solve for this last piece, I'm going to use equation D. Again, you could use equation B, because if you plug in a 0 here for A, this whole thing goes away and it's velocity times time, just like this, average velocity times time. My average velocity, though, is just my velocity because these two numbers are the same. So it's 15.65 times my time, 1.356, and my displacement, therefore, is 21.21 meters. And that would be my range, how far away it lands, 21.21 meters. Are there any questions about this example? Yes?
You got the VI from both for doing sine and cosine?
Yes. Because it's at an angle, you find the horizontal and vertical components of the initial velocity using sine and cosine. Okay. Any other questions? All right. I would copy this one down because this one looks a little different than the ones we have done so far. It says, James punts a 0.8 kilogram football. It has a hang time of 2.1 seconds and lands 51 meters down the field. With what speed did he kick the football? Okay, so he's punting it. He's obviously punting it forward because it lands 51 meters away and up. So he is punting it at an angle. They don't tell us what the angle is. In fact, they're asking us to find how fast it's going at the end. I know that he punts it with both an initial horizontal and an initial vertical velocity, but I'm going to have to figure out what both of those are in order to answer this question, because it doesn't say what's the horizontal speed he kicks it with, and it doesn't say what's the vertical speed he kicks it with. It just says what's the speed. And if you're asked what's the speed, it's asking for the resultant, that diagonal, the hypotenuse of your triangle. So we have to find both of those pieces in order to answer this question. So what do we know? We know the hang time. That's the total air time, so it's the vertical time to impact. So I know that's 2.1 seconds, and again, horizontally also 2.1 seconds. That's in the question. I also know that it lands 51 meters down the field. That is my horizontal displacement, so I can fill that into the horizontal column in that last spot for displacement. I also know vertically that if he punts it on level ground, and it doesn't say level ground in here, but my picture shows it being level. I should type it in the question too, but I know it's going to land at the same height from which it was kicked. And so I'm going to say that my vertical displacement, at least from launch to landing, is going to be 0, because it's going to land at the same height from which it was launched, or kicked rather. And then I know my acceleration vertically is negative 9.8 and horizontally is 0 meters per second. So I can fill all of those numbers in. What I don't know are my velocities. Okay, and that's what we're trying to figure out. So we have enough information this time on the horizontal side. Remember, these are the same velocity as each other. And I told you that if you know time and displacement, or if you know 2 of the 3 between time, displacement, and velocity, you can solve. Okay, and so we can actually solve for the velocity because we know the displacement and the time, and this is constant velocity, 0 acceleration. We can use the constant velocity equation, delta x equals velocity times time. It's that 4th one on my board, average velocity times time. It's just the average is just the velocity. So we're going to take our displacement 51 and set it equal to velocity times our time 2.1, and of course we can divide both sides. We know this, velocity is displacement over time. I could have written the equation like that. 51 divided by 2.1, that's my displacement over my time, gives me a velocity of 24.3 meters per second in the x direction. And again, that is a constant velocity, so I'm filling it into both of those, VI and VF, because it's the same the entire time. All right, so now we have the horizontal component figured out. I know how fast it's going to the right. I still need to figure out how fast it's going up, at least initially, in order to finish answering this question. So I need to solve for my initial vertical velocity. I have time, I have acceleration, I have delta y, I want VI, I have an equation for that, it's this one. Delta y equals VIT plus 1/2 AT squared. On my board it is the 3rd one down. And I can solve now for my initial velocity because I have those other 3 things. Plugging in, delta y is 0. We're looking for this VI. My time is 2.1 plus 1/2 times negative 9.8 times 2.1 squared. And that negative does make a difference, so make sure it's in there. If I go ahead and multiply all of this over here, 1/2 of negative 9.8 times 2.1 squared, all of that multiplied is negative 21.609. And so I'm going to add that number to both sides to cancel it over here. And now we have 21.609 equals 2.1 V. Divide both sides by 2.1. And we get an initial velocity in the y direction of 10.29 meters per second. So I know that value, I can fill it in. I can also fill in my final velocity at landing. If it's 10.29 meters per second here, then it's negative 10.29 meters per second here. If I want to fill that in, I can. I don't need it for this question, but I can. So I have everything filled in, but I still haven't answered the question because the question doesn't say, hey, what's the vertical speed or what's the horizontal speed? It just says, what's the speed? So I know that when the ball gets kicked, it has a horizontal velocity of 24.3 and a vertical velocity of 10.9. I need to figure out what the total velocity is, the total speed. But I don't add vectors like this. Okay, I add them head to tail. You're going to get the same answer ultimately, but I'm going to move it over here so I have them added head to tail. That way I can see the correct angle as well. I'm not asking you for it, but if I were, you would need to be able to draw it correctly to get the right angle also. So I have, again, my horizontal and my vertical components. If I want to solve for this hypotenuse of my right triangle, what equation can I use?
A squared plus B squared.
Yeah, a squared plus b squared equals c squared, the Pythagorean theorem. I don't know an angle, so I can't use it. But I do know, I could find the angle, by the way, but I do know this. A squared plus b squared equals c squared. I'm going to use 24.3 as A and 10.29 as B. If I plug those in, I have 24.3 squared plus 10.29 squared equals c squared. That's 695.68 equals c squared. Square root of both sides gives me a velocity of 26.4 meters per second. That would be the answer to the question. With what speed did he kick the football? 26.4 meters per second. If it said with what velocity did he kick the football, I would also need the angle. Okay, remember speed is scalar. I don't need a direction, but if it did say velocity, I would need to solve for the angle right here as well, which I'd have to use some trig to do. Before I go any further, does anybody have a question about this one? Okay. By the way, you could also solve this same question using the data to max height. It would also work. Okay, I would use half the time for that. I would say that my final vertical velocity was 0. I would still use negative 9.8, and I could still solve for my VI that way. You get the same answer. Okay, I didn't work it all out that way, but you could have. So you don't have to use the total data here. You could use the data to max height. Just make sure when you do that you use half the time. All right, follow-up question. Find the kinetic energy of the ball at max height. Kinetic energy, the equation for that is 1/2 mass times velocity squared, which means I need to know the velocity at max height. Guys, what can you tell me about the velocity of this football at max height?
It's 0. It has 0 final velocity.
It has 0 velocity? Vertically, horizontally, or both?
Vertically.
Just vertically. That means it is moving horizontally, right? The vertical velocity is 0, but it's still moving horizontally. At max height, there's only horizontal velocity. So if I want to solve for kinetic energy at max height, I just need to use the horizontal velocity and plug that into my KE equation. So KE equals 1/2 mv squared. Again, the velocity is not 0, it's just not vertical. It's horizontal only. So I'm going to use that number. 1/2 times 0.8, that's my mass, times 24.3, that's my horizontal velocity squared. If I solve for the kinetic energy at max height, I get this number, 235.92 joules. So it would be my kinetic energy at max height. Questions about this one? You're going to have questions like this in your assignment today, or, well, technically y'all started it last week, so you may have already seen them. Here's another follow-up question. Okay, what is the work done by gravity on the ball as it rises to max height? There are 2 different ways you could solve this. Work is equal to change in kinetic energy. I already know how much kinetic energy it has at the top. If I figure out how much kinetic energy it has when it's kicked, I could find the change in kinetic energy and get my work that way. Or I could do force times displacement, because work is also equal to force times displacement. I'm going to show you both ways, okay? But I'm going to tell you right now the first one's easier, okay? We can do it both ways, but the first one's easier. So let's do the first one first. Work is change in kinetic energy. This was my final at max height. It was 235.92. We just found that a second ago. My initial kinetic energy would be my 1/2 times my mass times my initial velocity. We found that earlier too. That's the speed at which it was kicked. It's the hypotenuse of my triangle. It's not in my table, but it's this 26.4 meters per second that's in my picture up here at the top. That was the first thing that we solved for. Yeah. Okay, so if I plug in that number, because kinetic energy or energy in general is scalar, it doesn't care about direction. We don't have to separate horizontal and vertical. We're just going to use that resultant. Okay, we get this. So my final was 235.92, but my initial's 278.27. I obviously lost some energy along the way. How much did I lose? Well, I can just subtract. Final minus initial, 235.92 minus 278.27, and of course it's a negative number, negative 42.35 joules, because gravity is causing it to lose energy as it rises. It is slowing down vertically. Okay, but it's slowing down. So my answer there for my work done by gravity is negative 42.35 joules. But I told you there were 2 ways to solve this, and this is just the first way. Does anybody have a question about this before I show you the second way? No? Okay. If you have one, you can ask me in a minute if you haven't asked yet. All right, so in order for me to solve it the second way, I really need to look at the data to max height, because the equation is force times displacement, and I need to know what the height is. I also need to know that the force acting on it is gravity. It says work done by gravity, but the force is the force of gravity, Fg. Okay, and so I can rewrite it like this. Work is Fg times delta y. And we're going to solve first for delta y so that we can then get work. So delta y is VIT plus 1/2 AT squared. We're going to use the numbers from the table. It's going to look like this. My initial velocity is 10.29 vertically. My time just to the top, it's half that total time, is 1.05 plus 1/2 times negative 9.8 times 1.05 squared. Gives me a max height of 5.402 meters. Again, this is why this one's harder. It requires us to solve for some more stuff before we can get it. The other one was just one extra step. So now I have my max height, 5.402 meters. I also, again, need to find Fg so that I can multiply them by each other. Fg, force of gravity, is mass times gravitational acceleration. My mass is in the question, 0.8. Gravity is negative 9.8. If I multiply those, I get negative 7.84 newtons. And so that's Fg. I have delta y. I can multiply them. So here's my Fg, negative 7.84. Here's my delta y, 5.402. Multiply those two numbers, you get the exact same answer. Negative 42.35 joules. You will get the same thing whether you solve it as change in kinetic energy or whether you solve it as force times displacement. My force here being gravity because we're in free fall. My displacement being max height because the question says what is the work done as it rises to max height. All right. So again, 2 different ways to solve that, and you can use either of those, whichever you like better. You're going to have some questions that are kind of similar to that in this assignment. So I'm going to ask you now to go ahead and finish working on your MyOpen Math assignment 702.3, mixed projectile motion problem set. It is due tonight by 11:59 p.m. So please get that opened up. I did change the due date. It should not be counting it late. If you have a question as you're working, let me know. However, before I have you guys do that, y'all are going to start an RA tomorrow. We were supposed to start it today, but obviously with the missed day, we're a day behind. I'm going to have you do one thing for me today to help you tomorrow. Okay, you're going to be working in groups of 2 or 3. I'm going to ask you to figure out who you want to work with now. Now, if they left the room, because we just had a couple people that had to go for pictures or something. If they left the room and you want to work with them, that's fine, claim them. But find yourself 1 or 2 other people to work with, and amongst yourselves, talk to each other because you need some supplies tomorrow. Okay, you need popsicle sticks, plastic spoons. I said to bring 2 just in case you break one, because that's what you're going to have to launch with. And then rubber bands. If you want hot glue, that's optional. But at a bare minimum, popsicle sticks, plastic spoons, and rubber bands. I would recommend hot glue if you have hot glue gun, or you can go pick one up. But again, you're building a catapult that looks something like that. So again, find yourself a group, figure out who's going to bring what supplies. If you have questions as you're working through the assignment, or if you have questions about groups, please let me know.